So shall we start now? Good evening,
Yes, sir.
everyone.
Yeah.
Yes. Good evening, all. Respected Dr. S.C. Samanta, convener DP Khandelwal Birth Centenary Celebration Committee. Dr. P.K. Samanta, HOD PK College Contai. Today's guest speaker, Dr. Rangeet Bhattacharya, Associate Professor from IISER, Kolkata. Dr. Pradeep Panchadhyay, other dignitaries present online, the participants, teachers, and student friends. We are very happy to have a second lecture of this series on applications of national workshop on applications of software to physics experiments. This is a second phase of program. First phase of program was on 27-28, and we are on the second phase of program. This lecture will be, first of all, let me welcome you all on behalf of IAPT, DP Khandelwal Birth Centenary Committee and PK College Contai. A very warm welcome to each one of you. And now I request Dr. PK Samanta to introduce our speakers today. Dr. Samanta, please.
Yes, ma'am. So, good evening, everyone. And it's my honor to present today's speaker, Dr. Rangeet Bhattacharya. So, in brief, Dr. Bhattacharya did his actually graduated from Jadavpur University and then moved to Indian Institute of Science, Bangalore for his master's. And then he also did his PhD from Indian Institute of Science, Bangalore with Professor Anil Kumar. He mainly worked on various methodological development in liquid NMR. Later, he moved for his postdoctoral research to Weizmann Institute of Science, Israel, and he also worked at Stony Brook University as postdoctoral fellow. And he mostly there worked on diverse areas of field, and most significantly the various applications of NMR methods in lithium-ion batteries and also on quantum rotors. And regarding his awards and honors, he was the recipient of the University Gold Medal at the Jadavpur University. He also received the R.G. Stone Fellowship at Weizmann Institute, Israel in 2005-06 and Feinberg Graduate School Scholarship in Weizmann Institute Science, Israel during 2006-07 and also the Laura Marinelli Award in 50th Rocky Mountain Conference on Solid-State NMR, United States in 2008. He joined Indian Institute of Science and Educational Research, Kolkata in 2010 as assistant professor, and presently he is there as associate professor. His present research is mostly on the dynamics of quantum systems, quantum computing, and beyond this research, one interesting thing, he is very passionate in teaching. And you know that a good teacher must teach, obviously, along with various kinds of demonstration. And he'll today he will be he delivered his lecture, rather it's a demonstration on application of PHYPHOX. Okay, so that students can use in their mobiles, so that you can have a very idea of how various kinds of software can be used, so that you can learn physics even you have only a mobile phone. Okay, so I hope you'll enjoy his lecture. So without wasting much time, I'll request Dr. Bhattacharya to start his deliberation. Sir, please.
Thank you very much for your very, very kind words. And I would like to also thank the organizing committee. I would like to thank Prabhat. I would like to thank Professor Samanto, Rekha. I mean, we have many acquaintances here. I see familiar faces all around. So, I mean, entire IAPT and the Prabhat particularly, I thank you all. So, it's a great pleasure to be able to interact with the students, I mean, which is something I enjoy. I mean, I don't know how much you would learn from me today, but I'm sure that I would enjoy the interactions. The big problem with this kind of setup, I mean, that we are forced to talk like this where we see only a part of your head, and you see my head like this, is because of this pandemic. And this pandemic has threw us in a difficult situation. Now you see, the pandemic is bad. We all know that very well, that we are all suffering various ways. Particularly, the problem is the experimental physics, or any experimental science. Earlier we used to go to the laboratory, we used to touch the instruments, do something, make changes here, make changes there, you record your data, and you analyze that, you write a report, and you learn in that process that how you measure a physical quantity. How do you determine, say, specific heat of a particular substance? How do you find a constant, say, for example, Planck's constant? How do you determine that? And it's not just the determination, it's not just the physical principle. The most important, one of the most important aspects of experimental physics is to measure it very, very accurately. Okay, it's not just, we measure something. We try to also measure accurately, and we specify, okay, we have obtained a value like, say, 10 plus minus 0.1. So we try to give you an accuracy of 1%. So this is one important aspect in physics, where we try to determine the physical values, or we try to look at the physical principles, whether they are accurate or not. In many cases, physics experiments also aim to look at, or rather try to establish a physical fact. Classic example is Michelson and Morley's experiment, which tries to determine whether we do have a speed of light constant irrespective of the direction of motion of Earth, and which eventually was a deciding result based on which the special theory of relativity was developed. So you see, in some cases we are not measuring a precise value. In some cases we are also distinguishing between zero and non-zero. Such cases are also experiments. The pandemic has created this problem that these experiments we can't touch. It's not just us research scientists or research students. For us, maybe we will get vaccinated, go there, but the colleges are off. So most of my young friends here, for you, it's a problem. You can't do what you used to do. So what is the way out? This entire lecture is basically to find a way out. So one way out is the smartphone, of course. I will not be much wrong if I say that we all carry a small physics laboratory with us. If you have a smartphone, which most of you do, if I'm not wrong. Now, what does a smartphone do? Of course, you take pictures, you take selfies, and you use this for social media interactions, check your mail, and of course the old-fashioned thing that a phone does, meaning making phone calls. So that is there. But that aside, there are many apps which help you monitor the sensors in a smartphone. Now this smartphone, look at it. It's basically a small computer. It's not just a small computer. It also has several sensors. It can detect light. It can be used as a light sensor, whether you have sufficient light or not. Lumens. It can detect sound. And because there is a powerful processor inside, it can detect the frequency of the sound, and it can detect it can tell you the spectrum of the sound, which frequencies are present. It can do all sorts of stuff. The most importantly, and probably most spectacular, is the accelerometer. So if you are moving your phone, it's accelerating, going up or down. It can very precisely measure what kind of motion is taking place from the acceleration. And you already know the smartphones have many fitness apps. What does this fitness app do? what they do is, as you move along, suppose you are doing an exercise or etc., all the time your smartphone is moving. So it is registering through the accelerometer that what kind of acceleration is taking place along X, Y, and Z direction. And from there, finding out whether you are walking or running or taking a step and doing some kind of exercise, it is possible. So that's what this fitness apps do. So what we thought, I mean, what not just us, many people thought, even before the pandemic set in, that with such a powerful device, probably we would be able to do some experiments, in the sense that there are so many sensors inside. If there are so many sensors, can we not use these sensors for, doing some experiments? It does not have to be at home. I mean, that's what the original idea, that you can do it. I mean, actually, since you're carrying your smartphone, why not? You can do experiments anywhere you like, as long as you set up a controlled experiment. I mean, controlled environment. So that was the idea. Many apps actually came up. These apps are available in Google Store, or if you are using iOS phone, Apple phone, then they are Apple Store. There these apps are available. If you install these apps, what you get is direct access to the sensor. So meaning, I mean, suppose I have this app in the smartphone, I switch it on, and I would be able to see the accelerometer data, how it's changing as a function of time. It's simple. So this is what I'm going to talk about today, is I'm using one particular app. I would like to do one experiment. I would like to show that you can do a rather complicated experiment. Earlier, you could do this experiment only in a proper physical laboratory, but now you can do it at home. That's the idea. Now, the title of the talk, it says measuring G. I mean, I'll be measuring acceleration due to gravity. This is extremely simple process. You do not really need a smartphone for that. You can make a simple pendulum and let it oscillate, and you can use any old-fashioned watch to measure like what is the time required for 100 oscillation. And if you have some rough idea about the length of the pendulum, that will give you a fairly accurate value of G. So for measuring G, you do not need really a smartphone. But what I'm going to show you, it's basically, you can say this is more like a proof of principle experiment, that we can do something complicated. And this is just a demonstration that way. So, I mean, without going any further, I would like to start sharing my slide, and would like to tell you about this precise experiment. And as for the asking questions and all, please feel free to stop me, ask question if you wish. I mean, although given a choice, possibly I would prefer that you ask all these questions in during the interaction session. Okay. So, I mean, but still, if you are completely lost, and if you feel that certain information you could not process and that requires immediate attention, please stop me and ask question. So I would like to show my slide, and it should be visible now. It should be visible now. So
yes.
Yes.
Thank you. You see, when the slide is up, I see only the slide. I don't see the Google Meet screen. So your verbal feedback is very, very important. Thank you very much. So we are going to find G, and we will use a smartphone. But before we find G, I mean, let's look at the working principle. Now, it's extremely simple. What we are trying to do is, it looks complicated, but it's actually not so. First of all, what we did here, we have created a pendulum. Okay, so there are, you see the two threads and this thick bar here on which I show by arrow the smartphone. It's basically the bob of the pendulum. Now, smartphone is an extended object. It's not a point particle. Normally, for a pendulum, we are using a solid ball as the bob. For that, one thread is good enough. But for a smartphone, usually you can make a cradle kind of shape. I will show you. And you can hang it by 4 threads so that it moves nicely. In this particular case, the smartphone is moving horizontally and along the direction of this double-headed arrow. So this smartphone is a pendulum and it's moving with VR, the velocity. Okay. And it is oscillating, let's say. Now you attach or you add next equipment. The equipment is laptop. So you put a laptop, it does not have to be a laptop. It could be another smartphone. I'm just showing you one laptop, just as a, basically what I did personally. So, here is my laptop and it's producing a sound, a monochromatic sound. Monochromatic in the sense, meaning this is sound of a fixed frequency. Let's say I'm producing a sound from my laptop at 400 hertz, very, very precise value. Then the smartphone, it's now a pendulum. Smartphone is oscillating. So suppose this smartphone, you set it up in such a way that smartphone is catching the sound from the laptop. Of course, you would say that because of the Doppler effect, it will hear a sound of frequency, a nu prime. Suppose the nu is the frequency of the sound which is coming out from the laptop at 400 hertz. What would be, how much would be the value that smartphone catches? Depending on the speed of the pendulum, it could be like 401 or 399, or it could be 402, 398. It will oscillate between these values. Now you would say, why oscillate? Okay. So before that, you look at this working formula. The different frequency that the smartphone is hearing something else is because of the Doppler effect. That old thing, ambulance approaching you, ambulance, the siren is on, and you get to hear, you sound certain frequency, and once the ambulance goes past you and it's moving away, and then you hear a different frequency because it sounds different. That is the old Doppler effect. We all know. This is not even. This is a +2 concept, to be honest. So what frequency do we hear actually? So what we hear is, suppose this is the apparent frequency nu prime that is equal to nu, and then 1 plus minus the velocity of the receiver divided by V naught. The ambulance case I mentioned there, the source is moving, the source of the sound is moving. That is different from what is happening here. Here, the source of the sound is fixed. The receiver is moving. The receiver is the pendulum. So when the pendulum approaches the laptop, then we use the plus sign and we know the frequency goes up while it's approaching, and while it's going away, then the frequency will be going down. Okay. So, this plus minus sign depends on which way the smartphone is moving. But the smartphone is actually not moving with a fixed PR. It's oscillating. So if it is oscillating, then we know the speed of the phone is changing sinusoidally. It is maximum, the speed is maximum when it's passing through the equilibrium position, and at the end, at either end, this end or that end, the smartphone stops and then it reverses back. So when it stops, the velocity is 0. So the velocity is actually oscillating. So which means this VR here is oscillating. Great. So if VR is oscillating and the changing frequency, which is essentially the difference between the frequency we hear and the frequency that the source emits. That will also be an oscillating function. The difference of frequency would be proportional to VR, and VR is oscillating. So the smartphone will hear an oscillating frequency and sound of oscillating frequency. So whatever it does here, say suppose smartphone catches something. The Firefox app, what it does is it converts this frequency to VR using this formula. It's straightforward, but you have to tell it what is the speed of sound. This formula is, you are familiar with this formula. This P0 is basically the speed of sound, and VR is the speed of the receiver. So, remember, we are talking about a very, very precise setup. Why it's precise setup? Because you see, V0, the speed of sound, it's typically, let's say, 340 meter per second. Okay, that's a big number. And what about VR? How fast it is? It's a couple of centimeters per second. Suppose the pendulum is really tall, like a approximate, let's say, 1 meter or 1.5 meter length. So in this pendulum, the smartphone is sitting there and it's oscillating. The typical oscillation is, if we calculate, it would be, I think, couple of centimeters per second. Not too fast. So couple of centimeters per second divided by 340 meters per second, it's very, very small change, extremely small change. So you need to use a good value of source frequency. Suppose I say the source frequency is 1000 hertz. And this VR by V0, if it is 1 by 1000, the maximum value of smartphone speed divided by speed of sound, suppose it's 1 by 1000, then this 1000 times 1 by 1000 is 1. So the change of frequency that the smartphone here will be 1 hertz. Fortunately, our smartphones are smart enough, thankfully, that they can hear and understand the difference of 1 hertz. At least we can check that. We can check that very, very easily. So this is basically the idea, that we will have a pendulum, and this pendulum, we will put the smartphone as a receiver, the smartphone, as the knob of the pendulum, and it will be a receiver. It will move horizontally, and the sound will come from a laptop coming in from the same direction. And as the speed of the smartphone is changing sinusoidally, the apparent frequency will also have a sinusoidal change, and we will find that out. From there, we will try to find the G. How do we find G from here? It's easy. There are two ways. You have already got it, idea that suppose we see we find this VR. This VR, suppose we calculate, then we will see the VR is oscillating. So the gap between, we can easily find out the period simply by counting that how many times, if we have a plot, then we can count that how much time it took to have 20 oscillation, and from there we can easily calculate the time period. And from the time period, it's easy to find out G. We know the pendulum's time period, and getting G from the pendulum's time period is straightforward. As I mentioned before, we're trying to do something simple like finding G by a very complicated method. But the core principle, why we are doing that, just to show you that how easily we can measure the Doppler effect. And we are just using Doppler effect for this one particular purpose. So, what are the equipments that we need? These equipments, you already have it at home. And I'm going to show you how I did it at home. I recorded some videos and images, and I'm going to share with you. So you need a smartphone that's going to I mean, it will be your receiver. You need another laptop. You need a laptop or another smartphone that is going to be your source that will produce the sound. In this case, source is static and receiver is the bob of the pendulum. That's the summary of your equipment part. Here is my pendulum. That's what I did. So I took a small box. Okay, it's basically box of a smartphone cover. You probably already guessed it. And then I'm hanging 4 threads. Okay, hanging from a rod. It's basically a curtain rod. I remove the curtain. The rod is there, and then I'm hanging 4 threads from that curtain rod, and just hanging this box. I just place the scissor on the box so that just to tell you when it oscillates, it moves along this direction, along the direction of the scissor. Okay, it's a very simple setup. It's actually done at my home. I mean, you can do that. I mean, you can easily do all of it's very simple, doesn't require anything special. Now our second equipment, PHYPHOX. How do you install it? I mean, PHYPHOX is an app available in Google Play Store. So you simply search PHYPHOX and it will show up. It has a very distinctive icon. I mean, install it. And once you install it, then these are the screenshots of my mobile phone with the PHYPHOX app open. It gives you access to raw sensor. Raw sensor in the sense acceleration without G, acceleration with G, gyroscope, light sensor, GPS data, magnetometer. And unfortunately, my phone does not have a barometer, but some phones have barometer. So if you have a barometer in your smartphone, then you can also have the pressure data. You already can appreciate it's enormously powerful. I mean, I wish there was a temperature sensor also. And I think there are external sensors available which can be plugged into a smartphone, and then there are apps like PHYPHOX which can detect the temperature from an external sensor, but I have not used it. So, okay. And there are many inbuilt features. Say, for example, under the section of acoustics, you have audio amplitude, audio autocorrelation, audio scope, audio spectrum. So what does it do? Suppose you click on audio amplitude, and then if you start the experiment, and suppose you are standing in front of a very noisy truck or some engine which is running some pump, it will catch that data and it will tell you what is the amplitude of that data. So, I mean, it's very useful, particularly if you are interested in knowing that among your friends, say, I mean, who can shout louder. I mean, I know it's not possible now because everybody is sitting at home, but still you get the idea. The amplitude of sound could be found out, or if you have a very funny application, I mean, a very interesting application actually, the audio autocorrelation. Suppose I have, I mean, suppose I have a situation where somebody is playing a flute and he's playing a particular note. So the flute is being played with a particular fixed frequency. PHYPHOX can hear that frequency and it can do the autocorrelation. So suppose the flute is being played and also some other noisy things happening such that I can't hear the flute properly. One advantage of autocorrelation is it gets rid of all the noise and it will give you a very pure data, which means the frequency of the single tone can be detected very, very accurately. So that is possible here. And of course, I mean, you can have audio scope, audio spectrum. So you record something, analyze the spectrum of the sound, which frequencies are present. You can do the Doppler effect, and this is what I did. So this is just one example. There are other things. I mean, you can also use it as a sonar. So it produces a sound and it comes back from the reflection. It gives you certain data. It has a tone generator. So that means you can replace the laptop by 2 phones with One of them, you click on the tone generator, you can produce a sound, and that sound, say, you did it at 1000 hertz, and you can move the other smartphone, which would be your receiver, and you'll be able to do this experiment easily. And there are others like applause meter, inelastic collision, centripetal acceleration, and many things. I mean, you can directly find out G by using this pendulum part. You can also put your PHYPHOX within a cylinder, and if the cylinder rolls, then it can give you the data, how fast it's rolling, and all other parameters. So there are other kind of stopwatch also, motion-based stopwatch, acoustic stopwatch. So stopwatch started, and whenever there is a sound, it will stop. The motion-based stopwatch. So I mean, like you start the stopwatch, and whenever you move your hand or something, you can program it that way that it will stop. It's very useful, very, very useful, particularly suppose you do it this way, that you start the stopwatch, drop your phone and catch it here, and when you catch the motion stopwatch, make sure that it stops, and you have very accurate recording of the time, how much time it took for the smartphone to drop. And from that also you can calculate G. I mean, I'm just saying, I mean, don't try this because smartphones are expensive. Now, there are optical and proximity stopwatch. Proximity sensor, if you have one, then it can stop counting if you have somebody nearby. So just a little bit of innovative way of using these sensors, and you have a complete physics lab with you. I think some of it will also be described. I mean, say inelastic collision. Here is an inbuilt experiment that if you have a ball, drop it on a surface, and it rebounds. Every time it rebounds, because of the inelastic collision, it loses some energy, and it will not come back to the same height from which you dropped. It will come back to a lower height, and then even lower, and then even lower. From this data, you can calculate the coefficient of restitution, and also you can find G if you know the height that this PHYPHOX can do. It can do a whole lot of stuff, but anyway, PHYPHOX is powerful, possibly we acknowledge that. And then let's move on to the next part. So how do we do this experiment? You open the Doppler effect screen. This is how it looks like. And what you need to do, you have to tell PHYPHOX that what is the original frequency which you started from the source. So what is the source frequency? In this case, the source frequency is 1000. So I was producing a 1000 hertz signal, 1000 hertz sound from my laptop. So I mentioned that it's 1000. And I left all other parameters unchanged, but the frequency range 10 hertz, it's typically the range it expects, 1000 plus 10 and 1000 minus 10. Because you see, when the PHYPHOX is recording the data, the sound is something analog, in the sense it's a continuous thing, but PHYPHOX, the sensor, it's a small digital computer, and the data that it records, it's basically digitized data. So when you record a data and digitize it, some of you already know about this Nyquist criteria and etc. So the sampling rate, how fast you sample, how fast you record the data point, how fast you record, like between 2 time point, you are recording time now, amplitude, time then, amplitude, another time, amplitude. So this gap between the point will tell you what is the frequency range that you can observe. So such range, tentatively we leave it at 10 hertz, because for a home-built pendulum, it never exceeds that frequency range. The time step is also mentioned, the 50 millisecond, and they are interrelated, so you can play with that. And the speed of sound, tentatively you have to mention. For our experiment, it does not matter much, but in many other cases, the speed of sound need to be given very accurately, otherwise the measured velocity will be wrong. After all, you remember the working formula had this speed of sound. So if the speed of its sound is wrong, then the VR will be wrong. And why it does not our result? Well, we are calculating the period of VR. So the amplitude of VR does not matter. So if V naught is off by a factor of a couple of meters per second, it's not going to affect our result. So I just set it at 340 meters per second. This is step one. This I did with my smartphone. So I'll repeat. The laptop is there. I open the smartphone and open Firefox. I set it up like this. Remember, I have not put it on the pendulum on the box yet. It's not oscillating. It's in my hand. Okay, I have not started the experiment yet. This is basically pre-experiment setup. Then what you do, you click on these three dots and you will have a pop-up menu, experiment info, export data. This export data would be very useful later. So remember, you can share a screenshot, you can have a timed run, and you can allow remote access. This is what is important for us because we would like to access the smartphone data from the laptop. So we click here. The moment we click here, of course, it will give a security warning because you are allowing your laptop to connect to your smartphone. And this is, of course, a dangerous security practice connecting to another device. So it will give you a warning and you can simply say, okay. Now, how does the connection happen actually? Well, what happens is this, there are two ways. So for example, at home, you have a wireless router. Then you can connect your laptop to the wireless router. You can also connect the smartphone, that your pendulum bob, to the wireless router, both connected to the same router. Fine. I mean, then this will work. But it may happen that you do not have a wireless router. Then what do you do? What you do is you can create, using one of your smartphone, a mobile hotspot and connect the other smartphone to that hotspot. So you are creating Wi-Fi hotspot and connecting the other one. Then also it will work. This hotspot can also be created from the laptop. So you have many possibilities. Just remember, both the phone should be part of the same network. That is very, very important. Once you have done that, then it will say the remote access is enabled. Access this experiment from the following URL. So if you open your laptop and type the URL HTTP and whatever it says, then on the laptop screen, you'd be able to see the Firefox app, which is running on the mobile. So if you want to click something, do something on the mobile, you can do that from your laptop. You do not have to touch the mobile. So this is important. So the moment you do that, then this is my laptop, and my laptop can see my Firefox mobile screen. You can see the setup window, and this is in the laptop. I can see it here. Okay, so I am accessing my mobile phone from the laptop. Next, what do I do? The next thing is simple. I take the mobile phone, I put it on that pendulum cradle, that box, I put it there, I mean, just at the place of the scissor, and I set a motion, so it's oscillating. I let it oscillate for a while. Why? Because if you have done experiment, you know that for a pendulum, oftentimes, particularly if it is not a single-threaded one, there will be some transients. The pendulum might wiggle. It's not moving in a single plane. So you have to wait a bit for these transients to die down. How do you know the transients have died down? Well, partly eye estimation, and at some stage you would be able to see that. I mean, when you think that it's moving smoothly, then you click here, the play button. I mean, it basically starts the experiment. Once you do that, then the screen will change and it will show you what frequency it's registering. this is my phone and this is the laptop. Okay. So in the laptop, I could see that there is this oscillations coming up. I mean, I will show you the video. Right at the moment, I am showing you the screenshot after the experiment. I have to show you what happened during the experiment also. That would be part of the demonstration. So right at the moment, it is oscillating. And look at this amplitude. Here it is clear. It's 1001.4, the maximum value in the scale, and the lower limit is 998.6. So here it is not visible, but it's the same thing. So as I mentioned before, our frequency change is typically 1 hertz of that order. It is even smaller, but Firefox did an amazing job of registering that small change in frequency and registering that oscillation. And from that, it did this calculation and it calculated the speed and what is the amplitude here. So it's moving from, there is a scaling factor wrong here, okay? I mean, not entirely, no, nothing wrong. So the speed in meter per second, it's basically the 0.5 and minus 0.5. So it's basically 50 centimeter to 50 centimeter. So you see the speed, I even had 30 centimeter per second, okay? The maximum speed. For how long does it have 30 centimeter per second? Very little time, very little time, because most of the time it was at the end. So most of the time of the oscillation is spent toward the end, you know, for the pendulum very well. So the highest speed is achieved only when it's crossing the equilibrium position. And also remember, the scaling factor is approximately correct, but not very accurately. My own estimation is it is wrong by a factor of 2. Okay. Now, there are multiple reasons. I will come to that when we discuss the error. I will come to that. But does it affect our result at this stage? No, because we are simply calculating the period. So this oscillation is what we are looking at. This is what we try to do. So this is after the experiment. So experiment is over. Remember, it's simple. You are looking at your smartphone. The smartphone is oscillating. You start the experiment. You click there. Once you click there, then the smartphone starts recording the data. So this graph gets dynamically adjusted. The data points are showing up. And then at a later stage, when you are done with the experiment, we click on the stop on your laptop. So it stops and you have your data. After that, you will have to export the data. So you will click on this 3 icon and you can export data. You can do that in your laptop also. From your laptop, you can click here, the 3 icon, 3 dots that give you the export window, and you can click and export your data. It gives you options. So here I have a zoomed up version of this result, the frequency and the speed. The speed, you see, it's oscillating nicely, and the frequency also oscillating here nicely. And this is what I did. Then after the recording of the data is done, so it recorded frequency, and from there it calculated the speed, and I exported the data. Now, I think the next one, before I show you that, you need to confirm one thing. I mean, do you hear this sound? Okay, so maybe, the yes. One problem with this video is it's creating a lot of sound. So I would like to show you the video from a different place. So what I would like to show you is this. Just waiting a moment. I'd like to share another window. So I stop presenting and I start a different window. Is it visible now?
Window is visible.
Okay. So this is my laptop, and here from the laptop I'm playing a sound of certain frequency. Then how did I do that? I mean, the easiest way is just searching web for online tone generator, and there are plenty of web pages which allow you to play a sound, and you can adjust the frequency from a sliding bar. So here I am selecting 2000 Hz. The bar is here, and suppose I play. So once I click there, and then you see, I mean, this is the Doppler effect app from the laptop. The mobile is already oscillating. So I clicked it, and it shows the frequency is oscillating. Now look at the mobile carefully. It's oscillating, and you can see the same window. It's recording the frequency and the velocity data. Both are oscillating, going on like this. The amplitude is small. But it's rather more or less uniform. I mean, when I try to do this experiment, I just have to make sure that it's moving nicely. I did not have to spend a lot of time in ensuring that it happens. You just have to let the transient die down. Once you have done that, then it's not a problem. It will smoothly oscillate. Now, you remember I mentioned that you would be able to figure out that whether your transients have died down or not. The way you do it is this. You can start recording, and then this pattern on the laptop will tell you whether you had transients or not. If you had transients, then you will not have smooth oscillation. You will have spikes, you will have noisy data, you will have a whole lot of trouble. So after the experiment is over, you can discard that portion of the data where you believe that you had transient. And you can analyze the remaining part where you have the smooth part. So this is possible. Now I stop it here and I go back to the presentation. Yes. Here it should show up now. Yes. Okay. So this is the data. This is the same data that we were watching. So it's basically oscillating. And then how do we analyze that? One analysis is simple. I mean, you can just expand and count how many peaks are there between, say, 100 and 200 seconds. So it's like you are counting 1, 2, 3, 4, 5, 6, and count how many peaks are there, how many periods, how many oscillations are there within a span of 100 seconds. And from there, you can find out what is the average duration of one period. And from there, you get the time period of the pendulum. If you have the time period of the pendulum, the length I already calculated. From that length, finding G is straightforward. And if you want more accuracy, you can also do, if you are using counting method, you can count from 50 to 100, how many oscillations are there, then 100 to 150, and then 150 to 200, then 200 to 250. So you have several set of observation, and you can take average of all these periods. That will give you a slightly better data. Or you can take the whole and do a Fourier transform. Now, Fourier transform can also be done by apps. And if you have a laptop, you can write your own program for writing Fourier transform. If you are interested, I mean, in the discussion section, I can show you how I did generate this particular plot. It's fairly straightforward. The Fourier transform gives you a certain other feature that simply counting the peaks here, the periods here between given a time span, that will not be enough. What you see here is the overtones. I mean, like the higher harmonics. Okay, this is your fundamental, and you have another, you have another, you have another. Okay. So where are they coming from? It's basically, you see, what did you measure? What you measured is how the speed is changing as a function of time. So this should have been a perfect oscillation, but you see there is a very slow frequency present. This is going up and coming down. If I continue for more time, you will see this. This is like a amplitude modulated data. Now, where does this amplitude modulation come from? There could be multiple sources. We will discuss that. The biggest suspect is the pendulum mechanism. If the pendulum is oscillating perfectly in a plane, then much of this oscillations goes away. So this is what I would like to discuss in the next part, how you optimize that experiment. But before that, I mean, just to conclude, I mean, in this slide, you can take Fourier transform, and that gives you a very accurate picture of what is happening. And you must choose the lowest non-zero peak. There would be a peak at 0 because this data does not have zero mean. Even if we set the mean at 0, still the data is getting truncated. And you are familiar with the Fourier transform, the properties. If you have oscillation and if you truncate it, and then you try to Fourier transform, then it's Fourier transform, the peak that you are supposed to get will be modulated by a sinc function. So if I zoom up the peak here, then I would be able to see the sinc-like oscillation towards the base. So fortunately, they are not very big, so I mean, can be ignored, but can be reduced if you can make the pendulum better. So the errors. You see, I mean, I mentioned right at the beginning, setting up this experiment is not a big deal. You can do this experiment. That is also not a big deal. What is the big deal is one of the important part of doing an experiment is to do it nicely, make it accurate. It's not just measuring a value. It is measuring often again and again to ensure that you have a repeatability. Things are getting repeated. Meaning, I mean, like, say, for example, look at something else. I'm measuring specific hit. I get some value. Next time I get hugely different value. Next time even another value. If the values fluctuate too much, then that gives you an idea that the experiment is not happening in a controlled environment, meaning we can't repeat the result. So this is very, very crucial. So if that also means that your pendulum will have to be set up perfectly. I mean, first time probably you do it for the like proof of principle case, the way I did. Next time you will change the cradle. You make a slight tinkering with the thread. Maybe you will find out that the regular thread, the cotton thread that I used, is not very good. A much better option would be a light metal thread that you can extract from a wire, AC wire. You just cut and take the insulation off, and these tiny wires that you have, those are very good because we are using multiple threads. That works very well. Then there are multiple issues with the sound. You can have a reflection from the wall. So say if you look at the setup, this laptop is here and it's producing sound. But suppose there is wall, then this sound will be reflected and it will reach the smartphone. So smartphone is catching the direct sound. It is moving this way, so it will catch one frequency. But look at the reflection. The reflected sound is reaching the smartphone, and at the same time, the smartphone is moving away from the source. Here, the source is the wall. So that will give you a lot of error. I mean, really bad signal. I'm not saying that it was not present in my data. I could not remove the wall. I mean, it's impossible. I could have definitely changed the orientation is a bit, but the curtain hanger, it's a curtain hanger. So I mean that rod, it is fixed on the wall, and then the wall at the right angle cannot be moved. Then what do you do? To increase the accuracy, of course, you can place some clothes, you can hang some clothes there. If you do that, the sound is mostly gets absorbed. It does not reflect that much, not like a flat wall. So essentially, you are creating an insulation kind of thing. So this is very, very crucial. If you reduce those reflections, then your result would be much, much better. Then there is a problem of the angle between the velocity and the direction of sound. So your smartphone is here and the laptop is there. If the level, they're not at the same level, then this is the direction along which sound is propagating. And laptops, I mean, your smartphone is moving this way. They're not collinear. If they're not collinear, then this entire formula which gives you the Doppler effect is wrong. I mean, not very accurate unless you replace it by a BR certain angle. Usually it adds a scaling factor. So this is the scaling factor which created the problem of estimating the velocity. I remember I told you that amplitude of VR, my RE estimation says it should be like 2, 3, 4 centimeter per second, and PHYPHOX telling me that it is like a very large value. Why it is so large value? I suspect it's something to do with this, the angle between the source. I could not keep them at the same height. And also the laptop speaker, I mean, I was not very smart that time. The laptop, I kept it, I kept it like this, and then phone is here. So laptop speakers, they're facing upward, the sound is going up. That's wrong. I mean, I should have kept it like this. But then you might also say the whole idea of using a laptop and laptop's own speaker, that is also not very good. I mean, you can use a dedicated speaker. You can take the line out, and instead of a headphone, you take the line out to a small speaker, and then it would be much, much better. Either that or two smartphones will give very good result, because the smartphones have speakers or MIC around this region. I mean, you speak like this oftentimes if it's too noisy, simply because you speak to the speaker. And also, I mean, there is, speak to the microphone. So that way it works better. Although I have not tried this, but I suspect it will give you a better result. Now, this experiment is extremely sensitive. Sensitive to what? Even it is sensitive to movement. You move your hand during that recording, you will be able to see spikes. So you need to be still, the walls are curtained, or in some way sound is getting absorbed, then it gives you very, very good result. So when you do this experiment, if you do this experiment, try to make it as good as possible, tinker with it. Just don't do it today and then leave it. I mean, that's not the essence of physics. I mean, try to do it as accurately as possible. Remove all distraction, try to get a nice pattern. And that would be, I mean, when you do that, it gives you a real nice, wonderful feeling. Okay, I have measured something with a good accuracy. At least I have created a setup which is great. The biggest advantage is you will be able to do it at home. You do not need to go to a library. Of course, I mean, this part I mentioned before, that there are other methods. You can directly get from accelerometer, you can directly get G. I mean, just open it and it will show you the value of G. You can drop still ball on glass plate. I think Dr. Anand Dasgupta will tell you about this, I mean, if you can. And then this record video of something moving and use tracker, which I think Dr. Minaj Hussain, he already mentioned that There are demo versions available for Tracker also. So basically, this is what I wanted to say, that smartphone is but a small laboratory, and you can do experiments at home. I mean, I'm not saying that it is replacement for laboratory. Of course not. In lab, you can do many other things. You do not have, you cannot set up experiments which use vacuum tubes. Okay, that is not possible. So smartphones will not give you, will not show you electron diffraction. It will not be able to detect Planck's constant in that method, that way. But anywhere a motion is involved, physical motion, you can use your Doppler effect, or a motion sensor or proximity sensor to do a lot of mechanics experiments. I mean, simple. If you have a good inclined plane and if you let it move, it's going down. And looking at accelerometer, you'll be able to clearly establish that g sine theta that we always use, that acceleration along this plane is g sine theta, theta being the angle of inclination. You can easily check that. Of course, it will not be accurate. Why? The friction is there, but it won't be much wrong. I mean, you can give it a try as long as you don't damage your smartphone, of course. So essentially, this is what I wanted to tell you, that the scope of the experiments have been expanded, and the laboratories have reached home. You can set it up there. You have a full set of sensors here. You are only limited by your imagination, not by equipments anymore. So, I mean, go ahead and do the experiments. So that's all I wanted to say. Thank you very much.
Thank you, Dr. Rangeet. The participants can interact with Dr. Rangeet. If anyone has a question, please unmute yourself and you can ask.
They can also write in the chat box, because
yes.
The one advantage of the writing in the chat box is I can go through the questions one by one and sequentially answer if they can. And they can also speak up and just ask the questions.
And I also request Shyam to see the questions on YouTube live streaming if there is any post. Shyam,
There
please.
is no post because there are only 5 people watching.
Okay.
Thank you.
Yeah, meanwhile, let me announce something. We had this program phase 2 continued on 6th and 7th October, but unfortunately one of the speakers, Dr. Ananda Dasgupta, is down with COVID, so we cannot have that session. But we have not cancelled, we are postponing that session. As soon as Dr. Ananda is well and in a position to take the lecture, we will arrange that lecture along with lecture by Dr. Panchadel, and we shall notify you through the groups or the other ways we can. So sorry for doing that, but we will be definitely back with those 2 lectures later at some time whenever it is convenient to both the speakers, and we will inform you. So participants, I think there are a few questions there.
There are questions coming in. I think the first question I have from Debabrata, if the object is in acceleration, so what can we do? I mean, Debabrata, what do you mean? I mean, like the pendulum, the receiver, it is moving. It's, of course, there is acceleration. It is accelerating. So, I mean, there would be acceleration. That's all right. And because of the acceleration, the speed is changing. Okay, and we are only measuring the speed by looking at the change in frequency. So, if it is accelerating, it's not a problem. The pendulum was accelerating, so will not be a problem. it will still work. It will still work. If you are trying to ask, I mean, suppose you are asking this question that suppose we are trying to measure, we're trying to look at the Doppler effect, and suppose a car is approaching us and it's accelerating, then what will happen? If the speed is not too high, if the speed of the car is still much less than the speed of sound, then you calculate the Doppler frequency, and there the Doppler shift will be a function of time. It will be kind of going up. Because, for an accelerating car, nice smoothly uniform acceleration means the speed is proportional to time. So your frequency will also be proportional to time. It is as simple as that. And then Ria, I thank you. You enjoyed it. The Bashanta Singh, it's similar to earlier Google Science Journal. Yes, it is. I mean, it's basically the same thing. And although it was developed separately, but it's very, very similar. And Dr. Prabhat, thank you very much. And Shushama Chakraborty, he has this question: is this process possible for mean fluctuation of energy in statistical mechanics? If possible, how is it possible? Are you asking whether the fluctuation of energy can be monitored or measured this way? Possibly not, simply because I don't think that the speed changes that much. Or let's say, for example, you have a pendulum. It's in mean position. It's fixed. Okay. If you replace the pendulum by a small particle, then it will do some oscillation at about the mean position. Why does it happen for a small particle? Simply because the air particles which hit the small particle and make it move, their masses are comparable. But smartphone is very heavy. So if it is in equilibrium, it does not do this oscillation, not in a visible way. So as such, most of the air collisions from all sides, they cancel out. So that will continue the directly. Okay. Srinivasa Rao, I thank you. And then Prashant, okay, thank you again to all of you. I thank you. I mean, Shushma, you say this is mean fluctuation of energy. I understand mean fluctuation of energy means mean fluctuation of speed also, because the energy fluctuating means most cases the kinetic energy is also changing. I mean, potential energy does not fluctuate much. Okay. And Sanjay, which is the best method for obtaining the value of G? Using accelerometer or measurement of free-fall time using acoustic stopwatch or Doppler. The best method, I mean, all are good. Possibly the accelerometer is the best simply because it is calibrated and you can start your phone and leave it on a desk and then it will not have any interference and it will give you acceleration due to G. The only trouble is how good the calibration of the phone is. I do not know. In most cases, we look at relative changes. Remember, this is one disadvantage of the smartphones is, although the sensors are there, but exact specification of the sensors, that how accurately they are calibrated, we do not know. But we can look at the relative changes. So in that case, if you drop your phone, free-fall acoustic stopwatch would be definitely quite good. That would be better than Doppler. Doppler is good, but not that accurate, I'm afraid. Now, Bashanta Singh asking, can we think of a mechanism to measure the wind velocity? Okay, you see, the trouble with measuring the wind velocity is we have to move something at the speed of wind. In the sense, suppose a wind's flowing some 20 kilometers per hour. So we have to move along with the wind, either source or the receiver. One of the instrument must move at that same frequency. That would be difficult. that will certainly be very difficult. At least I can't think of any quick answer to that. Okay, but thanks. I mean, it's an interesting. I think I answered the question.
Yeah.
More questions?
So if there are no more questions,
Okay. Cool.
may I request Dr. S.C. Samanta to please propose the vote of thanks. Thank you.
It is very nice to hear from Rangeet, but the problem is that, frankly speaking, I do not understand anything because I am not used to this smartphone softwares, etc. Even no softwares at all. But I rather trying to understand one problem: how the students are accepting these things. You see, because here the problem has been too much complicated.
Right.
Has it been simple Doppler effect? I think students should understand, but not only Doppler effect, it has the frequency is now oscillating. Not only that, but that concept is itself is complex. Again, amplitude is varying with time, so you are taking a Fourier transform. Most of the people, I think, doesn't understand that thing. Even if they understand that thing, they don't understand how computer can be used for conducting Fourier transform. So I think these things are complicated. I think that does not mean that students should not understand these things. But the point is that how do we understand that students have understood these things?
Okay.
So I think that should be a mechanism.
Okay.
This is my question. Because you see, yesterday Dr. Minaj has done that thing. That is also complicated, at least to me. To students, it may not be that much complicated. But the point is, again, that how we are organizing these programs for the benefit of the students. But if the students do not understand it, and if you do not understand how the students are understanding, then I think nothing is going to be achieved.
Absolutely,
so
I understand. So I would like to answer that. This experiment actually I gave as a project experiment in the previous semester to 120 students. Those are our students. Our students, and I asked them that you set it up and you do this experiment at home. So majority of them, majority means I think the number was close to 70, they actually set up something. Maybe I show you one example. One of my students, he set it up. How? I'll show you. This is what she did. I was very impressed. So this is what she did. She took the base of a stool and set up the pendulum exactly the way I described. Use some simple threads, put her phone there. She was using her laptop and she did it on the bed. And she was using a regular Redmi phone. Okay. So this is just one example. And let me try to get another one. Just one moment. Okay. Here is another one. I would like to share that too. I'm showing you because, I mean, like, just to show you how students responded to this before. I mean, this is from CK workshop. One of our students, she did that. She took very ingeniously the threads, okay, the shoeless actually. Shoelace and a board, and this was her the cradle, and this is the mobile, and here she used another mobile to complete it. So I mean there are many other examples. So far what I have seen, I mean the students, they are quite they respond to the smartphone challenges very nicely. The only trouble is the experiment must be set up in a way which measure relative changes, because as I mentioned, the sensors are They're very good, but we do not know how well calibrated they are. The only thing that we can measure are relative changes, periodicity in this case, for example, that can be done very, very accurately. So in IISER Kolkata, our colleagues, other friends, they are also exploring the other possibilities. So all other acoustic-based acoustic experiments. So far, the student reception is very good. Actually, it's not just the the smartphone or measuring G. It is just to inculcate the practice of doing something themselves, the fun of setting it up, measuring something accurately. Okay. If you say, did they gain anything by accurately? Did they measure G very accurately? Of course not. They can do much better using the regular pendulum and just by measuring the.
I understand. It is not for the measurement of G. Actually, they should understand many things. Not only the use of smartphone, the Fourier transform, so many things they would understand. That we understand. But the problem is that you have got in a situation where you have given this experience as a project to 120 students, and you have some satisfaction that actually a good number of students really responded to what we have done. But the problem is that it may happen that as the system is not that much calibrated, so results will not be according to as you expected. But the point I'm telling is that how can we know? In fact, there should be a mechanism of knowing the students' understanding. And I am telling that we should give some simpler problems, or this problem also can be given, and let us take the responses as you have done for your students.
Actually, I would like to respond.
Yes, please.
Like last year during the pandemic, most of us have started the online practicals. So when you include something in the practical syllabus and they have to upload it on the Google Classroom, because for practical work also we have prepared the Google Classrooms. That is like a journal, that reporting in a journal. So if we include these things, that use of a particular software or use of your smartphone for a particular experiment, maybe 1 or 2 experiments in the beginning can be included in the syllabus where they are using the smartphone or softwares, and then ask them to upload the results, like we have done it for NGP Part C experiments. NGP Part C experiments also, some of the students were not really well versed or acquainted with the softwares, but Dr. Minaz and the team took orientation training for them. And then we also gave them some exercises, assignments which were asked to upload on the Google Classroom, and from which we came to know that they have received something. So this is the only way that we can really talk about that, whether they have received. So it is, when you include that in the syllabus, I think it will be well received. Because whatever is within that frame, the students will definitely try to learn, if not now something else. Yeah. So, but it is now time has come that we have to adopt to this. Yes.
This, what I did. Sorry.
Dr. Aluwalia wants to talk something. I think.
May I say something, Dr.
Yes, sir.
From Shimla, and I was listening to your presentation very nicely, and it was great, I would say.
Thank you.
My simple question is, when you really designed this experiment, did you have some brainstorming session with the students to look for this kind of a format, say maybe online itself?
Actually, for this particular experiment, online there are already such ideas floating around that this can be done. I modified that idea, and plan initially was to design an experiment that our students can do at home. They were complaining, give us something so that we can set up at home and do something, anything. We are tired of online experiments. There are virtual labs like Amrita Vishwavidyalaya, where you can click and do the experiment, record data and analyze that. So such experiments give you very, very good feeling about how to analyze the data, but it does not give you any hands-on feeling. So they wanted a break. They wanted to do something. That was the motivation. The students were not part of it. But if you allow me, I would like to add two more things. I feel one way of testing whether the students have understood the smartphone-based sensors and their usage, and also meaning how do we ensure that they are actually coming up with ideas like you mentioned. These can be done if we give them projects. Projects in the sense, use the smartphone, use Doppler effect and measure something. I will not tell you how. You figure out how. Okay?
Yeah.
So that would be much, much better. Say, for example, a simple experiment which I was trying myself. How do I find the bat speed? I'm batting, cricket bat. I am hitting a ball, shadow practicing. How do I know what is my bat speed? So I thought of, securely attaching the smartphone there, doing a shadow practice, and while this Doppler effect is on. How accurate that is? It's not very accurate, unless the speed is exactly happening towards the laptop. But when I ensured that, I got reasonably good data, meters per second. The order of magnitude was perfect. I did not have any other method of finding out whether that data is correct or not. Okay, so but you get the idea. I'm still thinking of doing the regular thing in a different manner, but students can also do that. This is one way of finding out whether they understood the principle or not.
The second question is that you had such a huge data from 120 students.
Yes.
As a measured value of G, right?
Yes.
So did you really analyze that also to see that what was the, say, standard deviation and all such things?
No, because
so there was a lot of heterogeneity in your setups because every student was doing it in a different manner.
Yes. Yes.
So maybe that data could have been analyzed and you could have got some idea that this heterogeneity will, how much it will spoil the value of G itself.
It is the value of G that they calculated, and people who honestly reported, their values range from 9.2 to 10.5 meters per second square. Okay. It's
That's
a huge
good.
range.
That's really good. Not bad. That's not bad.
It's a huge range, and but most of them got something around 9.5. I could not find that why the value is not close to 9.8. It's less than 9.8. This part was not done. The problem is they are using different setups, so it's very difficult to characterize. Yes.
They were at different locations also, they may not have been at the same, height or something like that.
But that will contribute few centimeters per second square. Maybe it will make it vary from 975 to 985. But they got wide-ranging values. They also had the problem with, they mentioned that many of them, sir, the pendulum I set up, but the suspension, point of suspension is not rigid. So when this is oscillating, it is becoming a coupled pendulum kind of thing. This point of suspension is also shaking. What do we do? So, it was a lot of fun discussing these ideas, but each case is different. That was the biggest problem. Every student needs a unique solution. A generic solution do not exist because they are doing it at home. Everybody is different.
I think, Professor Ranjeet, you could have got them together again, maybe in batches of 20, and ask them that what can be the ideal situation to get best results out of it. That kind of an analysis would have been much better. That would have been a further exploration of the project itself. In fact, in the last 2 months, 3 months, also I had an opportunity to interact with the students at IIIT Barodara. And they were actually doing their labs through Amrita lab itself, the virtual lab. But they are, in terms of what has been given there, highly simplified, things.
Yes.
So we posed a challenge to them that within the scope of this simulation itself, what else you can explore. So that was the question which was given to each group, and each group was given separate experiment.
Very good.
So what further explorations can you do? So instead of, I was feeling that everybody will do all these things because procedure is given, everything is given. But we added that element that you must explore what else you can do. And that was the best part of, virtual labs. And there was one thing more which we did, a perception survey we carried out among the students. That how did they feel to do this experiment? And they still said, look, sir, we would definitely like to touch the real experiment. This is not enough. So their curiosity was still there to do the actual experiment. Thank you very much. I enjoyed it. But the other things you did, Fourier transforms and all such things, I think higher level students can definitely appreciate and understand those things.
But at plus 2 level, definitely we will try that. I would love to talk about that, a little computational technique which can assist the experiment. But today I think...
limited. We have limited time actually. It was just an introductory lecture, introduction of software.
Thank you, Dr.
Yeah. And moreover, even if they have, lot of errors in their experiments, but even if they try at something at home, I think they will enjoy something hands-on, rather than those only using ready-made simulations.
They started appreciating. Appreciating our lab equipments much more after they tried it at home, and they found even making a simple pendulum is not easy. You have to have so many considerations, and they were very, very appreciative of what they used to have.
Yeah.
The main keywords, ma'am, which Ranjeet has nicely mentioned, honest reporting. That is the prime factor, honest reporting.
Yes.
Ranjeet has mentioned. And in the chat box, Devabrata Das has written, I can't understand the Fourier transform part. And it is also my request. So I don't know whether it is possible today or not. From frequency analysis, why is Fourier analysis used in Doppler effect? I think many of the people here on the platform have the exposure on Python. So if you have 10 minutes or 5 minutes, you can show them using Python.
I will explain them without writing any program.
Okay.
So, Devabrata, about Fourier transform, it is a mathematical operation. Suppose you are recording data. What data? You are recording something which is oscillating, just like we recorded the speed of a pendulum. So we found the speed of pendulum is oscillating with time. Okay. So how does the data look like? The data has, if you write it down in your lab notebook, there will be 2 columns. The first column is time. The second column is amplitude. Okay. Amplitude of what? Amplitude of the speed oscillating. Sometimes speed is less, then the speed is growing. The particle is passing through the middle, the equilibrium position, the speed is maximum, then it is reducing, it's going the other way. It's reducing, it becomes 0 when the particle is at the end, then the speed is negative, it's moving the other direction. This is how you got the data. Of course, you can't do it by hand. We are using PHYPHOX for that. Okay. So suppose this is your data. How would it look like if you plot it? If you plot it, I showed you, it will look like something which is oscillating. Now, Fourier transform is a method, a mathematical method, numerical method. It's basically an operation that gives you the frequency of the data. So if you have a nice single sinusoid, You take the Fourier transform that gives you the frequency with which the sinusoid is going up and down. So if you have a perfect sinusoid, you get a Dirac delta-like function, very short peak at the position of the frequency. So position versus amplitude, that data after Fourier transform, it gives you intensity versus frequency. So x-axis is frequency, and you have intensity. Intensity where? Intensity of the frequency that is present in your data. Suppose your data is oscillating at 10 Hertz. Then in the frequency axis, at the position of 10 Hertz, you will have one peak. If you have two frequencies, 10 Hertz and 15 Hertz, and you do the Fourier transform, you will have two peaks, one at 10 Hertz, the other is at 15 Hertz. This is what we call a spectrum. Okay. So in this case, I tried this. It is not essential, as I mentioned, but Fourier transform works like this. Fourier transform gives you the frequency content of your data. How many frequencies are there and to which extent? Some frequencies there which is less, another frequency is there which is mostly contributing to the spectrum. So it gives you the frequency at the position, at the right position. I do not know, I mean, whether I explained well, but mostly this is what it does. The remaining part, I can show you in coding, but not today. I mean, today it's a bit late.
Nice. Thanks, Ranjeet. Nice.
We can have a separate session on computational physics. And
Maybe. Yes.
can be included. This can be one of them. Yes. Yes. Can we go over to Dr. Samantha for the vote of thanks? Dr. S.C. Samantha.
We have already at 9 o'clock p.m.
Yes.
If there is no other question, then we can stop now. Thanks to Ranjeet for a very nice presentation.
So, thank you. I mean, I thank you all, and it was really very, very enjoyable experience from my part. So I would like to thank you and
Thank you, everyone. Actually, on behalf of IAPT, we would thank the entire team of PK College Contai, especially the technical team, because they are actually, on their toes to have such kind of programs, and everything went on very well without any technical problem, I think, last 2 days. So a big thank you to the technical team. Dr.
Contai Science Academy is also there.
Yeah, Contai Science Association. Yes, thank you. So both are really deserve the vote of thanks actually, and Dr. Pradipta for coordinating things very correctly, nicely, because you were the key person to coordinate between DPK, BCC and CAS actually, CSA. So, Dr. Samantha, any comments you would like to have?
No,
because we have already announced the postponement.
Madam, just based on their effort, exercise and capability, we are conducting this program.